So today we're going to talk about two related topics, which are kernels for classification and clustering for pattern detection. And what makes them related topics is they both share this key idea of exploiting similarity between your data points. First, we're going to talk about how this idea of similarity can be used for classification. And the general approach originally when people were thinking about classification was either to try to learn a model or to try to reason directly from your examples. Reasoning directly from your examples is called case-based learning. And you can think of this approximately how law in certain countries works. You have this exhibit before you and you want to know, is this a 3, is this an 8? And one thing you could do is you could build a perceptron, you could build a naive Bayes model, or you could look through your original data and say, well, what does this most look like? Oh, it looks like this thing I saw back in 2004, and that was a 3. And then you could maybe clone that answer. Be a very different way to go about classification. And where it might seem particularly appealing is in cases like this. If you remember, in the non-separable case, we saw what the perceptron does on this kind of data, which is, it never quite manages to find a separating hyperplane that gets the entire training set correct. And you might think this is an anomaly, but in fact, this is the norm because there's some noise in your labels and generally your features aren't perfect. And so you could imagine various fixes, we talked about some, where you kind of make some stab. You draw some line that more or less gets as many things right as possible and it strikes some compromise, but is never quite able to get the data perfect. Part of the reason why we can't get the data perfect here is because we're drawing straight lines and there's no straight line that works. So, case-based reasoning. In fact, the key algorithm here is called nearest neighbor classification. And the idea is we start from similarity. So, over here on the right, we have some example points. So we have a positive point here, a positive point here, and then there is a negative point here, which in this case, positive is white and negative is green. So given these points, you might say, well, what line should I draw? Instead of drawing a line, you could say, any other point I pick that I want to predict, I'm just going to see whether it's closer to one of my pluses or one of my minuses. In the case of one nearest neighbor, what's usually just called nearest neighbor classification, you find the point that's closest to you and you clone its label. There are extensions to this, like k-nearest neighbors, that can be more robust, where you find the k nearest neighbors to you. So you walk out of your house, you see who's to the left and right, and then you do some kind of vote. This helps if, for example, a couple of the points are labeled incorrectly. You don't want a little basin around them that is also going to be labeled incorrectly. So this smooths things out a little bit. The key idea here, in order to get this classifier working, there's no perceptron updates, there's no mistake vectors, there's no independence assumptions in a naive Bayes model. This is all driven by, one, your similarity function. And that's the heart of it, really. Because that basically takes the role of your features. That tells you which examples you're like. And then there's this issue of k, right? Should you have a small k where your neighbors are very close to you? Should you have a big K where there are many neighbors to get an accurate pooling of the votes, but where you might have to kind of reach further out in the space and some of your neighbors aren't so much like you anymore, right? You can think about this guy here. Right? If he only uses one nearest neighbor, then he's going to grab whatever's right next to him. But if he pools, then he's going to start eventually getting some of the 2s as well. So this is a trade-off. The amount of k should remind you of things we've seen in other classifiers. Right? Essentially, this is a hyperparameter here, and you would have to tune it on held-out data in order to find the optimal number. This idea also brings out one of the important points in modern machine learning, which is the distinction between what's called parametric classification and non-parametric classification. The word parametric means having parameters. And so a parametric model is something like a perceptron or naive Bayes, where we have weights or probabilities or some fixed set of numbers that summarizes your training set. How come we only have 2/3 of our screens? We'll never know. Okay, so a parametric model has a fixed set of parameters. In the perceptron's case, that was the weights. Those are the things that got updated as you made mistakes. In the case of naive Bayes, that's the probabilities that you extract from your training set. As your training set gets bigger and bigger and bigger and bigger, what happens to these weights and these probabilities? They might get more accurate, but they don't become more numerous, right? They're still the same set of features. They're still the same set of conditional probabilities. And so more data means better settings, but not richer classification boundaries. In a non-parametric model, the complexity of the classifier actually increases with the data. And that means okay. The complexity of the classifier increases with the data, and that means in the limit, this actually is more powerful. Okay, in the non-limit, where we all live, sometimes it's worse. So let's see an example of this. Let's imagine that I have some actual two-dimensional grid. This is why we have redundancy. Okay, so let's say we have an actual two-dimensional grid. And there are some pluses and there are some minuses. Here there are pluses in circles. And I want to make a good classification on any point that might fall. So let's say I have two examples. And maybe on my examples, here's one plus and one minus a circle. Well, this is a reasonable boundary to draw, not only on the basis of a linear classification, but this is also the boundary of who's closest to each of them. Right? If you've only got 2 points, the boundary of who's closest is going to be a line. What happens as I get more points? In the perceptron case, this line would move around in response to the errors and try to strike some balance and get as many things right as possible. But in the nearest neighbor case, I don't know if you can see these dots very well. Let me make them bigger for you. In the nearest neighbor case, if this is where my examples fall, then this is my decision boundary. So it's very nonlinear. It's some kind of Voronoi thing that tells me I get the label of whatever's closest. So what's great about this is if the underlying truth has this weird shape, I'm starting to learn the weird shape. What's bad about this is the underlying truth does not have a weird shape, I'm starting to learn a weird shape anyway, right? Because I'm really closely following where my sample points happen to fall. I'm not kind of regularized by knowing what's important and what's not via my features. But as I get more examples, now here I won't draw them all for you, but you can see that the classification boundary is starting to take on, maybe it's an irregular shape, but it's certainly not a linear shape. And if I get more and more examples, eventually I will reproduce the underlying truth. And here's what that was all generated from. So the truth is something that you're not going to be able to do very well with a linear classification on these features, right? If you have better features, it might become linear. And given a ton of points, you eventually just learn what the whole space looks like. In between, you might want to have some image like this in your head. What you've lost from the parametric classification is the ability to draw these clean lines. What you've gained is the ability to draw any shape. So you can draw any shape badly. So how does this work in practice? Well, let's say, take the digit example that we're going to be mostly using today. So we take some new image. So here's the image we'd like to classify. What we did with the naive Bayes model is we computed its conditional probabilities using Bayes net inference. What we did with Perceptron is we took some dot products and picked the biggest one. And what we're going to do now is we're going to compare it to a bunch of training examples. So we're going to say, okay, how about you? And some similarity function is going to say, not similar. And then we'll go to compare it to this one. And it'll say, oh, reasonably similar. And then we'll keep comparing them. And maybe the most similar one is this one. And if the most similar one is that one, we'll say, well, you're most like that example. That example was a 1, so are you. Okay? That's pretty cool. There are some issues with this. First of all, you still have to decide how to encode your data points. And maybe here the encoding is just kind of the raw encoding. Maybe we won't do a lot of featureization of any kind. And here the vector might just be the raw intensities of the grid strung out into a single vector. But then we need a similarity function. And while the encoding may not have been rich in its representation of the important properties, the similarity function has to be. The similarity function has to tell me what is it about two-digit images that makes them similar. So what should I use? I've got these two vectors. How do I tell whether they both look the same? Right? I want I want it to be similar to this one and look nothing like this one. What do I do with my vectors? I mean, I used to make features and compute conditional probabilities and all that. If I gave you two vectors, how would you tell if they were similar? What? So you might look at the difference of them and see whether or not point-wise they have a big difference. That would be more of a difference. If you wanted similarity, you could do something very related. You could take their dot product, right? If you imagine they're normalized, if their dot product is 1, what's that mean? It means you've got your hands on an identical vector. And if their dot product is 0, it means they've got totally different pixels lit up, right? So the dot product is some kind of measure of pixel overlap. So that seems to make sense. If the dot product is high, then they should have a high similarity. And maybe we should pick the example that has the highest dot product. Okay. So that's nearest neighbors. Really, it's all about similarity functions. So if you just go around taking dot products of your raw examples or something like that, if you're trying to do spam like this and you take the dot product of your of some representation of your document, it might not work out so well. Even for digits, though it seemed appealing in this case, just taking dot products of raw things usually won't work. So if you want to make this kind of stuff work well, you need a smart similarity function. And just like in practice with a perceptron or naive-Bayes classifier, most of the work in the real world making it work well is coming up with good features. Most of the work in getting something like k-nearest neighbors to work well is coming up with a good similarity function that encodes what you know about the domain. Now on the surface of it, you might think, isn't it easier to write down features than come up with similarity functions? By and large, that's been true. By and large, it's been true that more people use the kind of parametric approaches, but it's not always true. And vision is a good case where the dominant successes have come from similarity functions rather than features. All right, so similarities might be based on feature dot products. So instead of just taking dot products of inputs that you think of as vectors, you might pre-process them by extracting numbers of loops and connected components. Now you still got a vector, it's just kind of a better vector, and now you can proceed to take dot products. But you could also imagine somebody just handing you a black box similarity that does something awesome. Let's think about an example of that. So you don't need to know about the specific similarity function, but I want to give you a sense that it's not just about some raw encoding and a dot product and maybe calculating some connected components. So here's an example from computer vision. So let's say you wanted to identify that these two 3s are similar, right? So you'd like their similarity to be high. The problem is these are actually points in some 256-dimensional space that tells you which pixels are on. And it might well be, like if you look at these, do you think these have high or low similarity? As a human, they look pretty similar. How about as a dot product of their actual feature representations? It might be kind of low, right? To look at a more extreme example, what if it were 1s? What if it were, well, the 1 was like this, and the other one was like, I don't know, I'm left-handed, so my 1s come out kind of like that, right? You say, oh, those are similar. They've got like 1 pixel in common. So this raw dot product isn't invariant to things that we know preserve the shape. For example, scaling it a little bit, zooming in, zooming out, moving it around, rotating a little bit, having thicker strokes, and so on. And so what we'd like to do is compute some similarity function that's robust to that stuff. Each of these kinds of invariants requires some work. I'll just tell you a little bit about one to give you a sense. One of these is that you could say, well, I don't want my similarity to be dependent on the exact rotation. And so what I could imagine doing is instead of just taking the two images and taking the dot product, I could think about them as some point in a space which can be rotated around some axis. That means what was once a single point, so here's your 3, now becomes a rotatable, it now becomes an entire curve that represents all the rotations. And if I've got 2 of these curves, then I can look for kind of the point where they're closest. That basically boils down to rotating the one until it has maximal overlap and taking that as a similarity. That's really hard to write down as a set of features, but it's really easy to think of in terms of your knowledge about how the vision should work and be invariant. Yep. You anticipated my next question, which is, what about 6 and 9? Well, maybe it shouldn't be that invariant to rotation. Okay? So if you let things rotate arbitrarily, sometimes this is good. Like, if you're doing object recognition and you've got a cat and you rotate it upside down, like, it's not an alligator, right? It may be less likely to see an upside-down cat, but, you know, it's probably still a cat. 3s, maybe you're safe. 6s and 9, you're in trouble. If you wanted, you could say, all right, well, rather than saying a 3 is this whole curve of all the rotations, you could instead say, here's my actual 3 right here. And instead of looking at the curve, you could look at this kind of tangent line. And you could say, I need to be on the tangent line. That allows you to kind of do small rotations, but not big ones. It's a little weird because as you rotate a little more, you start kind of like getting into things that aren't really 3s that have extra lines, but nothing looks like that, and so it's not a big deal. Basically, you just want to confine yourself into a region of tolerable rotation. You could also imagine having a similarity function that penalized the rotation, so that as you rotated, it became more expensive. All kinds of things you could do. And if this stuff appeals to you, the place to learn about these kinds of ideas and techniques is 280, the vision class. You can do this in entirely different ways. So you could say, I don't want to rotate my images. I want to take some idealized 6. So, you know, maybe here's an ideal template of a 6. And then when I get my pixels, and the pixels are shown down here, I don't know how well you can see them, they're the little circles. I'm going to take each of my templates of 6, 7, 8, and 9, and I'm going to try to kind of warp them to match the pixels as well as possible. And I'll say, okay, I need to deform my perfect 6 a little bit to get this, but it's not too bad. And then I didn't do much deformation, and I still covered all of the pixels. But like, if I try to take those pixels and cover them with a 7, you know, I get a mess, right? 7's all distorted, and it still doesn't cover the pixels. You could do this whole computation, and you could start thinking really hard about how I get my templates and what's the cost function for deformation. In the end, you just get a similarity function, and the nearest neighbor does its thing. Okay? So all of the fun here is in the computation and development of a similarity function. Any questions on that? So what do we have now? We've kind of got two approaches. We've got things like nearest neighbor, which get to use these fancy similarity functions that let you encode things like rotation invariance that would be very difficult to represent as features. But there's no real learning, right? You just look and see what's the closest single point. The whole idea of the parametric learning was kind of cool. You took all of your data, and together it taught you something beyond what each individual point might noisily represent. On the other hand, excuse me. On the other hand, you have these approaches like Perceptron that are parametric that do explicit training. You try to figure out what is the setting that reduces my error. But you can't use these fancy similarity things. You only get these linear dividers. Or can you? So it turns out you can actually combine these things, and let's see how that might work. But first, any questions about the similarity-driven stuff? Okay, quick test of understanding. Which of these will be faster to classify a new point? A perceptron or a k-nearest neighbor classifier? Nearest neighbor, why do you say nearest neighbor? What? Because as soon as you find your neighbor, you know the answer. Okay, how do you find your neighbor? You take your new point, and what do you do with it? You compare it to the first example, and then the second example, and then third example, and how many examples? All of them. That turns out that's actually super slow. With the perceptron, you say, okay, here's my weight vector for class 0, dot product, done. Here's my weight vector for class 1, dot product. You do 10 dot products, and you're done. So in general, provided the normal situation, which you've got tons of examples in a small number of classes, it's actually going to be very slow to use nearest neighbor, because you've got to kind of poke at every single example. You haven't abstracted from your data in any meaningful way, except insofar as your decision boundary might vote or something. The computation, any abstraction that happens, happens at classification time. Okay? Everybody believe me? So this is one thing you should know in the back of your head. Nearest neighbor may work, but it's going to be deathly slow. So let's take that slow thing and stick it somewhere. We're going to do what's called kernelization. We're going to find a way to take our perceptron, which had this good property of learning which examples were informative because they prevented mistakes. And what we're going to do is we're going to embed these similarity functions so that we can still learn which examples are important, but we're going to represent our knowledge about the examples in a way that keeps the similarity functions as a black box. So when a new example comes around, we're still going to compare it to all the inputs, but now there's going to be some perceptron magic that's going to tell you which inputs actually matter for your decision. For example, you might learn that some of them are noisy, that some of them are more kind of central than others, and so on. Okay, let's take a step back. Let's remember how perceptron worked. So remember the perceptron algorithm was, one by one you pick up data points. It was an online learning algorithm. You try to classify your data point with your current weights. If it was correct, you do nothing because those weights look pretty good. If it was wrong, you do an update. What was that update? You kind of took your feature vector and you added it or subtracted it to various weight vectors. Can everybody remember that? So let's think about the output of that process. Can the final value of a weight in a perceptron learning algorithm be an arbitrary real vector? Or do I know something about the set of vectors I might end up with after running the perceptron? Well, I know something about the set of vectors I start with. I start with a 0. Okay. What do I do to Mr. 0? How do I modify it? I add things. What do I add? I add data points. Sometimes I subtract data points. What that means is that every weight vector I've got in a perceptron came from summing up a bunch of inputs. Which inputs? Basically the ones I made mistakes on, because those are the important ones or the hard ones in some sense. So I imagine for any given class, or for the binary case, there's only one of these. You started off with 0, and then you made some mistake where you should have predicted this class for x1, and so you add this feature vector for x1, but then you accidentally predict this when it's not appropriate for x5, so you subtract the feature vector for x5, and you go along doing these updates. So in the end, every weight vector is a sequence of adds and subtracts of inputs. Okay, believe that? That's kind of the critical thing here, is that these weight vectors aren't arbitrary numbers, they are linear combinations of your inputs. And maybe that makes sense, because you might think the weights are kind of an average of the inputs in some way. You know, that's kind of right. It's an average where the weights and the average depend on the mistakes you made. That means I can write any weight vector that came out of the perceptron algorithm, binary or multi-class, like this. Let's unpack this notation. This says that the weight for class Y is a sum of a bunch of input examples, their feature vectors. We sum over every input I, and we add it into the sum with some constant alpha. This alpha is for a specific input I and a specific class Y, and it essentially counts how many mistakes were made for that input and that class. Okay, so alpha IY here would be, +1 for that mistake we made on that class Y and that instance 1. Most of the time, what are most of the alphas? They're mostly 0, right? Most things aren't in this sum, unless you've just made kind of mistakes on everything everywhere. So we can write this linear combination mathematically, but we should have in the back of our head that many of these alphas are actually 0. What this means is if I wanted to do the perceptron classification, where I take my weights and I do a dot product with my feature representation, I can keep my weights around and just do the dot product, or I could be a little bit lazy about it. At any time, if I keep track of these update counts, right, the number of times I made mistakes on each instance and class, I can kind of reconstitute the weights on the fly by using this. You can think of this equation here as the perceptron reconstitution formula. It says if you tell me the updates you did and you give me your examples, I can recompute the weights by adding things together with the right linear combination. Okay. There's a fundamental equation here, and we're going to kind of need it for the rest of the lecture. So, any questions on that? Okay, so let's think about what we did with a weight vector in the perceptron algorithm. Well, the input was x, and it had features f of x. There were various classes y. For digits, they were 0 through 9. For each class y, we computed a score. So the score was a function of the input x and the possible class y. For each class y, there was a weight vector. It's shown in green here. And we took the dot products, and whichever dot product won, that was what we predicted. That was the weight that was most similar as a vector to the feature vector we're trying to classify. Now, if we have the weight vectors, great, we just do these dot products. But what if we didn't? What if instead we were relying on the reconstitution formula? Well, then what we would do is we would say, all right, before I take the dot product of the weight vector, which is what I've learned, with the example that I'm trying to classify, I have to really quick reconstitute the weight vector by adding up all of the linear combination of the examples xi. So you see how the only difference here is that the bottom one is slower, right? They do the same thing. It's just we're rebuilding our weight vector on the fly out of the examples. Why would you do this? You should never do this. Okay. But it unlocks something. It lets us regroup terms. Rather than taking a linear combination of the inputs and then taking the dot product of that with the feature vectors, we can instead take a linear combination of the dot products directly, because dot product is a linear operator. That means we can rewrite it like this. This tells me that if I want to find the score for an input x with feature vector f of x, I compute its dot product against all of my training examples. Okay, what are those dot products? Those are similarities. What did nearest neighbor do? It took the biggest one. What does the perceptron do? It takes a linear combination of them. So essentially, rather than looking for the biggest one, it's looking for the appropriate combination of them, where the appropriate combination is learned from the errors we've made. So right now, we've essentially got a nearest neighbor kind of approach, but it's buried in a perceptron, so we don't treat all our neighbors the same. Some of our neighbors are more informative than others. But you still shouldn't do this, because it still does the same thing as taking the dot product of the weight vectors. The reason why this is powerful is you can replace this dot product with any black box that takes input x and training example xi and tells you how similar they are. So now there's no feature vectors anymore. There's no dot products, or at least on the surface there aren't any. And we've got a perceptron that works just given a similarity function. Now, of course, I can only do this if I've learned the counts alpha, but this is cool. I can now classify, instead of by taking a dot product with a weight vector, which requires kind of size of output space, many dot products. This requires something more like size of output space times number of data points, many computations of the similarity function. So the thing on the bottom is much, much, much slower, but it unlocks this arbitrary similarity function. Okay. So we can now run Perceptron without features. All we need is a black box that gives us similarities. So here's the algorithm. This is called the dual or kernelized perceptron. This idea of kernelizing a classification algorithm is a very big idea in modern machine learning. It doesn't just apply to the perceptron, but it more or less applies to every algorithm in more or less the identical way. So once you have the idea with the perceptron, kernelizing an SVM, or if you learn about logistic regression, it's all a very similar process. So here's the algorithm. You start with 0 weights. Well, that's what you did before, except we don't have weight vectors anymore. And that means instead of starting with a 0 weight vector, we start with all the alphas, the mistake counts, as 0. We still pick up the training instances one by one. When we pick up a training instance, we try to classify it. How do we classify it? Well, we pick the class that has highest score. The score is no longer a dot product of weight vectors and the example. It's now a linear combination of kernel functions, similarity functions, based on the mistakes we've made. So we classify. Well, we're either right or we're not. It's still the perceptron. So if we get the right class, our weights, such as they are, our process of combining kernel functions using mistake counts seems to be working, so we shouldn't change. What do you think we do if we make a mistake? We can't change the weights anymore. What can we do? All we've got is these alphas. We can write down that we made a mistake. So in some sense, this is a simpler update than it used to be. We used to say, oh, you predicted Y. You were supposed to predict Y star, so you were bad. take your weight vector for y and subtract off this feature vector, take your weight vector for y star and add on this feature vector. The effect of that was to make the prototype for y less like this example, and the prototype for y star more like this example. And the analog of that in the dual case is just to say, all right, well, I was supposed to guess y star, so up its count. I made a mistake on it. And I accidentally guessed y, so lower its count. Same update, except instead of adjusting the weights, we adjust the mistake counts. If we then did a reconstitution of the weights, we get the same answer as the normal perceptron, but there don't actually have to be feature vectors to reconstitute. So this thing's called the Kernelized Perceptron. Somebody gives you a black box, right? That's these guys in the drawing. That black box tells you what the dot product, effectively, the similarity is between two examples. And this lets you run your perceptron. The upside, you don't need to be able to phrase the features. You can just jump straight to the dot product or similarity. The downside is every time something goes into this perceptron, it has to check its similarity against all the training data. Now, of course, that's not so slow if you don't make too many mistakes, but the more mistakes you make, the slower this has to be because the more things you add to the linear combination. And this actually tells you that if somehow you had a classification algorithm that used fewer alphas, that had fewer of these examples supporting the decision, that would be better. And if you remember back to support vector machines, they had this property, only things on the boundary mattered. So this can be a little bit faster if your algorithm is smart about keeping the alphas, the dual vectors, sparse. Still going to be super slow. That's why very often in practice, the power of this is not used in practice, it's just too slow. Okay, so who cares? This was basically a strange way of doing a very simple calculation, unless we had a powerful similarity metric. What's called the kernel trick, if you continue on with machine learning, says, actually, you know what? Any similarity function can act as a dot product, right? Because we saw originally that dot products were a good similarity function if we had good features. And this basically says that any similarity function can be thought of as a dot product between some kind of features, even if in practice there would have to be infinitely many of them, or you couldn't write them out. Now, this is a little red asterisk. Why did I do that? I did that because there's like a ton of fine print on this. There's some technical requirements that your kernel has to obey in order for it to actually be representable as a bunch of features. But to a first approximation, this is there's a result that says the right kinds of kernels can actually be thought of as high-dimensional feature vectors, even if you personally don't know what those feature vectors are. And that's a powerful thing. This lets us learn new kinds of hypotheses. In particular, it means your decision boundaries don't have to be linear anymore, because they're not operating in some two-dimensional space. They're operating over the similarity space, which kind of who knows how many dimensions that has in practice. Okay. Any questions about that kernel stuff before I talk a little bit more generally about nonlinearity? You're going to see nonlinearity not just today, but also in the next lecture on a topic about decision trees. But for now, let's think about nonlinearity just as this problem of your learner is trying to put a fence that separates the positive and negative examples in your training set. Now, the reason you put this fence is so that you'll do a good job at deciding positive and negative on other examples you haven't seen. And if your actual training set boundary snakes around, you might want your fence to snake around like this. That's not something you can do with a linear classifier. So Perceptron wasn't able to do this. We just saw one way of increasing the power of our classifiers, which was to go to a kind of data-driven way. And since data-driven case-based reasoning tends to put a little bubble around each example, you saw that it gives you nonlinear separators. So that's one way. Another way, and in practice the way nonlinearity is usually tackled in the real world, is to say, if it's linear, great, and if it's not linear, rather than going to some fancier algorithm that can draw curves, or even a non-parametric method because they're so slow, instead you should just add enough features that suddenly it becomes linear or separable. What does that mean? Well, let's say we have this example here. Right? It's just a one-dimensional example. It's linearly separable, right? Anywhere I draw the boundary between kind of -1 and +2 will separate my data. Now, algorithms are going to differ on where they draw that line, right? But it's separable. You might decide, for example, to put it equally between these two. That's what a support vector machine would do. But here's a data set you can't draw a line for. We already saw one solution. Say, we'll do nearest neighbor. Nearest neighbor would be slow, but you have a blue region and 2 red regions, right? Suddenly you're free of the shackles of linearity. But there's another way to free yourself and lift yourself up, and that's add another dimension. So if you just add a second feature, which in addition to x here, or whatever this feature is, we add x squared, well, now our data looks like this. The data has now been embedded in a higher dimensional space, and now is it linearly separable? Yeah, you can kind of draw a line here. So what does this line look like in the original space? It looks like kind of a blue region surrounded by 2 red regions. Linear in the high dimensional space, but not in the projection to the lower space. This is essentially how you work things in practice. Your data's too hard to classify, so you add better features. You can't tell the spam from the non-spam. They've got all the same kinds of words, but then you add in a feature that says, is this person in your contacts list? How many people just received this? And now suddenly in this higher dimensional space, you can slice through these two things. Spam's on this side, ham's on the other. Was there a question? General idea about this approach is you can always get away with linearity. You just might need to add features that put you in a space where linearity does something fancy. So for example, you want to classify the central region versus the outside. You can't do that with a 2-dimensional line, but you can do it with a, you can't do it with a 1-dimensional line in the 2-dimensional space, but you can do it with a 2-dimensional plane in a 3-dimensional space if you add another axis which kind of squares the distance from the origin or something like that. Now that looks very abstract, but really what it says is, hey, look, here's my example. X and Y aren't informative. Distance from the origin is. Let's add that as a feature. Now you're living in the space on the right. Okay, so we've seen multiple ways of handling nonlinearity. Excuse me. One is stay really close to the data and draw these wiggly lines around your examples. The other is add new features. And the other is kernels, right? Well, kernelization kind of you can think of as doing both, right? Because it's a similarity function, you're staying around your data. But because mathematically, though we didn't go through this, mathematically you can think of a kernel function as being a dot product in a high dimensional space. It's essentially doing what's drawn here, but in a way where you can't actually write down the space off the top of your head. So it's really all the same idea. You'll see a different idea with decision trees that's about segmenting the space in a kind of adaptive way. Okay, so to sum up about kernels, why would you use these? Can't you just add these kind of mystery features that separate high dimensional things on your own? Like for example, you might want to add all pairs of your existing features. You can do that explicitly, or there's something called a quadratic kernel that lets you do it implicitly. Like yes, in principle, you can just add your features. And in practice, that's exactly what people usually do. You don't need to modify your algorithms, but you could end up with a lot of features if you require a very high dimensional space. There are some kernels, like the kernel that looks at your distance in Euclidean space and then exponentiates that, that are very hard to represent explicitly. So kernels let you do these things. They let you do things like the vision similarity metrics, and that's a very powerful thing. People only use it really when it's the only choice because it's so slow. Okay, so we're going to change gears a little bit now. Just to set up where we're going, we've just talked about classification, and we'll talk about it a little bit more in the future. Classification systems are supervised learning. You see some evidence, and you make a prediction. And we've seen several methods for this. This applies when you have labeled data. And so essentially, you train your classifier to memorize the data, but generalize in the appropriate way so that it can handle new inputs. Okay, this looks something like, I don't know, this, right? These are supervised learners, right? They went to class, they received examples, and now they are generalizing to new instances. Final exam time. Unsupervised learning, clustering systems, do something different. They take unlabeled data. They take your examples. Your examples don't have the right answer stamped on them. And instead, these systems try to detect patterns. They group the documents together and so on. So you might want to group emails. You might want to find categories of customers. You might be looking at program executions and which ones are anomalous or malicious. This is good when you don't know what you're looking for. You're just trying to take all this data and organize it. It requires data, but it doesn't require labels. The downside is it is very often the case when you run a clustering algorithm, at least for the first time, you get crazy stuff out, right? Suddenly your email comes back not ham and spam, but like, you know, stuff that was sent in the morning versus stuff that was sent in the afternoon, right? Those have very different hours on them, for example. And you're like, well, that's not really helpful to me. I didn't get the clusters I wanted. Okay, but in general, clustering systems are about unsupervised learning. You pipe the data in, and the system figures it out. That's like this. Okay, so we're going to take a break, and then we're going to talk about a simple approach to clustering and how we can relate it to what we've seen so far with similarities. Okay, before we talk about, sorry guys. Before we talk about clustering, I want to show you something even more awesome than clustering. What could be more awesome than clustering, you say? Answer, the final contest. Okay, so some of you may know about this from before, but it is very different and I believe more awesome than in past semesters. So here's the board for the final contest. It's 2 teams. It's basically capture the flag. So there's a red team and a blue team. You write code for your agent which controls 2 pieces. So you get two ghost things. There's a red side and a blue side. Let's imagine you are the red team on the left. When you are on your home side, you're a ghost. So you can't eat dots, but why would you? They're your dots. And if any invading Pac-Man come, you can eat them. You will also have to go to the enemy side, and when you cross the boundary, you become a Pac-Man. Now, when you're a Pac-Man, you're vulnerable to ghosts, but you can eat dots. Your goal is to eat all the opponent's dots. The new trick this semester is that you don't just eat them, you pick them up, and you have to get them back to your side. So if you are killed while carrying the dots, you essentially explode in a pile of gory dots. So I'm going to show you an example. These agents are not particularly good. These are basically the agents for the last version of the game. As we have better and better staff agents for you to go up against, we will be showing you examples. And what we'll be doing is starting in a few days when this is live, you'll be able to start working immediately. We'll have a ladder. You'll be able to have matches, nightly matches, and there will be rankings. And we will have, we'll release a description of how extra credit and achievements and things like that are tied to your performance in these nightly rankings. So among other things, it's good to get started early while the staff agents are still crappy. Okay, so let's see what happens. Let's see a game here. Too much loud. Okay, let's see the game here. So the agents make, in this case, kind of a rush towards the other side so they can become Pac-Man and eat some dots. Okay, you can see when they die, they kind of, it's kind of violent. Yeah. So you cannot just blitz or you explode like that. And blue wins. You don't have to eat all the dots, just most of them. Okay, so that's the game. I'll maybe show you the, I'll show maybe at the end if we have a second, I'll show you the game again. But keep that in mind. Oh, I guess what you didn't see in this particular example is that board was the consensus ground truth view. What your agent sees actually has a fog of war. So you need to do tracking as well. Okay, clustering. How can I talk about clustering after the capture the flag game? All right, well, what's clustering about? Clustering is about you got a bunch of these objects, and you're trying to put them in piles of similar things, okay? So you could imagine doing this using not an algorithm, but your human vision system. For example, here are some two-dimensional point patterns. And I say, okay, let's look at the one on the left. If we look at the one on the left, and I say, put that into two groups, you might look at it and you might say, this one and this one, right? And if I say, put the one on the right in two groups, what would you do? Well, you might say, top snake, bottom snake, right? Okay, now, who's to tell you that you shouldn't do left snake and right snake? Well, kind of intuitively, as a human, that doesn't seem right. But, you know, it's not that crazy mathematically. And this is one issue with clustering systems, is it's unclear that there's even a single right answer, or that if you have an answer in your head that the algorithm's going to come up with it. In any case, it's all going to depend partly on your algorithm and partly on what similarity means. One option that's easy for similarity is to say similar things have small Euclidean distance. We could talk a lot about different similarity metrics, but for now, let's just take this one. Let's imagine we have points in some vector space, and things that are similar are close together in just an unweighted Euclidean sense. We're going to see an algorithm called k-means, which you may have heard of. K-means is a pretty simple algorithm. It very well would be the thing you came up with if somebody told you to cluster these things. But it actually has the key idea of just about all the clustering algorithms that people have come up with since. So in k-means, we have two concepts. We have data points, and here those are shown as balls and they have colors. And then we also have means, which represent the clusters themselves. And those here are shown by these little robots that are collecting the data points. In this example, the blue dots that you see in these little clouds are the data points, and the red dots are the cluster centers, the means. This is probably not a very good positioning of the means. However, the clustering algorithm goes like this. Pick k random points as cluster centers. There are variants of this. How you pick them, trying to make them diverse, trying to make them cover the space. Maybe you only want to pick points that are actually data points. For now, let's just imagine it's random points centered at 0 with some distribution. So you pick k random points, and you alternate. In one step, you assign data instances to the mean that is closest to them. So that looks like this. Each of these red points captures the data points that are closest to it. Then you look at the set of points assigned to a cluster, and you move the cluster center to the center of those points. In that case, these centers are going to move, right? You iterate this and you stop when no points assignments change. So let's look at an example. Okay, in this example, the important thing is the colors, which represent the assignments. The boxes don't represent anything here. And the dark colors are the means. The lines represent where that mean will go in the next step. So for example, look at Mr. Red down here. Mr. Red, the center is at that dark point. The set of red light points are the ones that are currently assigned to it, meaning they're closer to the red mean than anything else. And this point here that the line is pointing to represents the center of those light red points, which is where the mean will move when it's updated. So let's watch this algorithm proceed. First, let's observe that the cluster centers are in terrible places, right? Green has captured 1.5 clusters, and there are 3 means all sitting on the bottom center cluster. Initialization is generally going to be very bad. But let's watch what happens. What's going to happen to the red guy? Let's watch him for a second. He's going to move over to the left. And so now essentially he's competing for this cloud with the black mean, which has more of the cloud. Also look at the green center. The green center has essentially one cluster in the upper right that it's got a lock on and no competition, and it's got a cluster here in the center that it's competing with purple. So it's going to move up, and watch the red guy, I think, is the most important thing here. So red's up here competing with the black, but as green moves up, purple starts to lose ground to red, and red ends up actually taking the bottom cluster and leaving the other cluster to the black mean. So it actually ended up in a pretty good space. Let's start with that at the beginning again. So here, it's a mess. And the red mean kind of doesn't know what cluster it's going for. It kind of moves over, and then it moves back. But in the end, they kind of push and pull, and you end up with a reasonable clustering. You don't always end up with a reasonable clustering. Yep? How do you choose how many clusters to make? There are decades of research on that, and the short answer is nobody knows. There's a very complicated probabilistic answer to it. It's not actually clear that answer even works. The short answer is you don't know. One of the many things about unsupervised learning that is not really solved. So there's this k-means algorithm. I just described the algorithm. It's really simple. You assign points to the closest mean, and then you assign means positions to the average of their points, and you iterate until it stops. There's all kinds of things you worry about, like how do you initialize it, how many clusters is it going to stop, like that kind of stuff. But you can view this and answer some of those questions by thinking of this as an optimization problem. So for example, let's define here by phi the total distance. So phi is a function of the points, which are fixed during this algorithm, right? They're indexed by I because there's a lot of them. A, which is the assignment, it's also indexed by I because each point is assigned to one of the clusters. The assignments change every step. We also have the means, which look like data points. They're points in the space, but there aren't very many of them. There's one per cluster. They're indexed by k. The quality of this assignment can be found by summing over all of the data points and looking how far that data point is from the cluster it's currently assigned to. So sticking clusters and kind of sticking means in the right place tends to lower this, and assigning points to the closest mean tends to lower this. And in fact, the algorithm I sketched for you lowers this quantity phi every time. So there's two stages. You update assignments, which means you fix the means C. So these are fixed, and the assignments are updated. And in the other one, you fix the assignments and you update the means. You can think about that procedure as doing coordinate ascent on this quality function, where you first change the assignments coordinates, and then you change the means coordinates. This basic idea of doing coordinate ascent between some kind of parameters, the means, and some kind of predictions or latent variables, which are the assignments, that's actually a key idea in a very large number of clustering methods, including the expectation maximization algorithm, of which k-means is actually a very special case. So how do we know we're actually making progress? Let's think about the two phases. In phase one, we update the assignment. So we take each point and we reassign it to the closest mean. That's these little robots handing their balls back and forth. So let's say we have this setting here, where the arrows indicate assignments from points to means, and the colored squares are the location of the means themselves. Well, there's some points that are pretty far from their closest mean. So if we added up the distance, we get a big number. If we take each point and individually, independently point it towards the closest mean, well, the assignments would shift. It should be pretty clear that this lowers the total distance because each point went to something that is either the same or lowers its distance. Okay, so that's pretty easy. This step lowers the total sum of distances. How about when you update the means? What do we do there? We take the means themselves, fixing the assignments, and we set the mean to be the average of all of the data points currently assigned to that cluster. So what's shown here in the diagram is if you have some mean which used to be kind of purple, but now it's holding a bunch of red points, it's going to become red. So here, if these are the assignments, where should, say, the green mean go? Well, it should kind of move to here, right? And it should be green, not purple. So it should look like that. It seems intuitively reasonable that this is also improving our quality, but less obvious. So why is it that assigning the means to the average of their points can only decrease the total distance? Well, it's a fun fact about Euclidean distance, that if you can write out the calculus if you want to prove it for yourself. The point with minimum squared Euclidean distance to a set of points is their arithmetic mean. Okay, so what does this mean? We have an algorithm. It's guaranteed to decrease this quality function in a coordinate ascent style. We have to initialize it, And that can be a tricky thing, right? If we initialized here, what would happen? We'd more or less instantly get the right answer, right? What happens if you initialize somewhere else? Well, what can go wrong? It matters what you pick. You could get the wrong answer. You could initialize here. Do a little thought experiment in your head. What is the final clustering going to be? Well, very quickly, blue is going to capture this point and then basically sit there. Green's going to capture this point. Red's going to capture these points, and then it's going to stop. So this clustering isn't very good, but it is a stationary point of this algorithm. This algorithm is only local search. Okay. There are various schemes for preventing this. Detecting that one of the clusters has a lot of variance and splitting it, initializing a bunch of times, trying to initialize so that your initializations never had points close together, because it's kind of a recipe for this. In the end, though, this quality function, it's non-convex. It's got lots of kind of local bumps. And when you do coordinate ascent, it's a kind of a local search. And you're going to stop somewhere that may or may not be optimal. Okay, here's a view of k-means actually getting stuck. It looks a lot like the example. Essentially, 2 points are sharing one cluster, and one cluster is kind of 2 means are sharing one cluster, the green and the purple, and the blue mean is basically captured 2 clusters. Yeah. You know, maybe you would want to here split one and merge the other or something like that. So why isn't this like the beginning, right? The beginning of the example I showed you looked like this, but then everything worked itself out, right? The reason why it could work itself out is because there were kind of a bunch of points in between, and purple could slowly eat those points and kind of drift to the right. There's essentially no path in this optimization to get there. These clusters are too well separated, so you get locked into what you're doing pretty easily. You know, sad robots. Okay, let's ask some questions about k-means. Will this converge, or will this procedure run forever? Well, it should converge, right? There's this quantity you're lowering. There's finitely many configurations you can be in, and kind of you can lower it, and you eventually just run out of configurations, and you can't be raising it, so you can't cycle. So, modulo some ties where it stays exactly the same, the sum of these distances will converge. In fact, k-means tends to converge extremely fast. It tends to be something like logarithmically many iterations, sometimes even faster. So it converges really fast. Maybe that should worry you, like things that run really fast. Yeah. Okay, does it converge to a global optimum? Like, no, we've already seen that. It doesn't converge to a global optimum. That actually means 2 things. It both means it doesn't globally minimize the distance function, and it also means that even if it did, it wouldn't necessarily give you the clusters that deep down in your heart you wanted. Will it always find true patterns in the data? No. What if the patterns are very, very clear? No, but it is more likely. Will it find something interesting? Maybe. Do people ever use it? Well, it sounds pretty grim so far, but yeah, people do use this stuff because it's discovery, right? It's a tool you use for looking for patterns. You can run it again and again, and you look at the results, and if it occasionally gives you some insight, great. Now, there are cases where you actually can run these things live and have them be useful enough to deploy, but sometimes they're just for exploration. Sometimes clustering works, but it doesn't work right out of the box. You need to change your similarity function, you need to massage your data, you need to get a better clustering algorithm. It's not always kind of k-means and vector spaces. How many clusters to pick? Well, you guys asked me this question. Kind of no one knows, right? You could imagine kind of saying, well, as I add more clusters, what happens to my distance metric, all else equal? Goes down, right? If you have clusters everywhere, then everybody's close to their closest cluster. So somehow you can't just look at the distance metric, which actually turns out to correspond to a likelihood function probabilistically. You can't just look at that, because then more clusters is always better. You need some penalty for the number of clusters. You could have a method to balance the penalty for clusters against the gain in distance metric. And sometimes if you look at distance metric, if you have like kind of some number of clusters and then kind of your total distance, sometimes it's like distance is really, really high and then it plummets and then it's really, really low. Sometimes you can see a kind of natural number of clusters. Usually you can't, and usually as you change your penalty, you just kind of drift up and down in the number of clusters, and now you're still answering the number of clusters, except now you're answering it by deciding how harsh your penalty is. It's a very hard problem. There are other kinds of clustering methods. I only want to say these very briefly because they have some advantages in practice, and I don't want to give you the sense that everything is based on alternating optimization, though in practice that's maybe the most important class of these methods. So in agglomerative clustering, you take individual points and you kind of smash them together. And then you take these big kind of popcorn cluster looking things and you smash them together until eventually all your points are together in one big cluster. And along the way, you've made some decisions. So for example, you might have a bunch of points. And you say, well, I don't know what clusters they're in, but I know some of these points are extremely similar. Let's just merge them. So for example, we might have an algorithm that says, maintain your set of clusters, put each instance in its own cluster, and then pick the two most similar clusters and merge them. And so clusters kind of grow and grow and grow. So for example, you might pick these 2 points and merge them. Then you might pick these 2 points and merge them. And then you might pick that single point in the blue and merge it with the points in the red. As you do this, you're going to build what's called a dendrogram. You're going to build a series of merges that eventually results in one big, giant, happy cluster. Now, you probably don't want that. You already know what all your data points are. And typically, you cut this process off at some point. This is nice because your clusters contain subclusters. This can do weird things, like you can start with 1 point and add all the other points one at a time and get something very uninformative. But this is another kind of clustering that gives you a little bit more information. Not necessarily better clusters, but more information. Now, the key thing here is, what does it mean to say whether two clusters are close, right? 2 points is easy. You gave me a similarity function. If you give me a bad similarity function, you get bad clusters, right? But here, let's say I've got 3 points in one cluster and 3 points in another. How close are these two clusters? Well, there's a lot of options. You could take the closest pair, that's shown here. You could say 2 clusters are close if they've got any points in them that are close. They could be close if they have the farthest pair. And these two things have very different properties. If you use farthest pair, you tend to get kind of big spherical clusters. If you use closest pair, then you tend to get long stringy clusters. Because with closest pair, you can take a long stringy cluster and add one thing onto the end. But that would be really expensive for farthest pair. You could do some kind of average. In practice, average actually doesn't work so well as a variant. The dominant thing in practice for getting decent clusters are things that look more like something called Ward's method, where what you do is you measure the sum of squared distances to the current means, and then when you put them together, you imagine creating a new purple mean, and you look at the sum of squared distances to that, and you look at the difference. And essentially, that's the function from k-means again, except now we're optimizing it in an agglomerative way. One nice thing about doing that is it gives you another answer to the question of the number of clusters, which is, how many clusters should I have? All numbers. You start with 1,000,000 clusters, and you end with 1 cluster, and you have all of the answers in between. And you can cut that wherever you want, or you can even have, something where you explore up and down and try different points. Any questions on agglomerative clustering? Okay, here's an example of classification and clustering. If you use Google News, I was actually going to update this, but then it kind of struck me that things haven't changed that much. In any case, what happens when you do a search here in Google News? Well, you'll notice a couple things. First of all, there are categories, like world and business and politics and things like that. Secondly, individual stories are like little clouds of, documents from different news sources. So what's going on here? Well, the top level categories, that's supervised classification. There's just some fixed set of these. And that's good, because if you have a fixed set of them, you can go into your preferences and you can say, I like politics, but I hate the world, or whatever. That's classification. You get training data, and then trained supervised classifiers stick stories into these buckets. However, the grouping of stories, that's more of an unsupervised clustering approach. These two things are very similar. Sometimes it's very easy, because documents are often kind of rewrites of an AP release that people are sharing across sites or something like that. But what you'll notice in this is there are kind of 2 mistakes that can happen. A whole story could be in the wrong place, or you could have a story that, yes, it's a story about business, but like one of those 3,000 articles is actually totally unrelated, but maybe contains some of the same words. So that's what's going on here. And of course, in any deployed situation like what Google News has, there's a lot of other stuff going on to make sure the interface is good and that the quality of the clusterings improves over time and things like that. One interface issue is, for these clusters, it wouldn't be very useful browsing if you just basically got told, okay, here's a cluster, it's documents 573, 812, and 6,000,002. You'd be like, I don't know what that is. So what you get here is you get a kind of summary of the cluster. Essentially, this summary, the snippets that describe either kind of the top-ranked document or some mixture of the documents and the picture that's selected, that's all labeling the cluster. So this is another problem with clustering, is even once you get these 1,000 documents that you think are similar, you still gotta like describe them to the world. You gotta propagate up some common keywords or pick a representative, which is what's going on here. Any questions about that? Yep. Yeah, it's a great question. How do you pick representatives? There's a lot of, this actually gets into another issue of document summarization, which is that the representatives themselves are too long. Now for news, you get this actually nice thing for summarization, which is news articles are written, essentially journalists are trained that their story may be truncated at any time, so it needs to have the prefix property that any subset of it has to be coherent. So essentially the first couple lines is a pretty good summary in many cases. But there's a question of which document do you pick, which sentences do you pick from that? Do you pick one that's closest to the mean? In some sense, basically yes. But you do want to be a little bit careful because you don't want to pick a document that's kind of one super long sentence that just has a keyword here and there. And so you want to mix in other factors as well. So you want to have some notion essentially of utility. Great question. Other questions? All right, I'm going to leave you with this game so that you can look at it and imagine what your agents will do to defeat agents like these, which are in fact the default agents that are shipped with the download, and so if you can't beat these, that's a problem. I mean, you could basically beat these 50 times by using these. One key thing these do not do is they have no sense when they have so many pellets and just need to go back. Oh, he exploded. I love the exploding dots. This is awesome. Oh, there it goes. There is actually a shoot the moon option, which is if you eat all of the dots, you don't have to return with them. Okay, so everybody start thinking about that. That will be released fairly soon.